Now so far in this course, we have seen basically two ways in which you can digitize the signal. One was flash, wherein you compare the input with all references in one shot. Second was SAR, in which you did this binary search program, right? And it turns out in practice these are the only two algorithms we follow to actually digitize the signal. Now on top of this, we do have a couple of techniques to increase the speed or the resolution further. So that's what we look at in the rest of the course. So from now on, whenever I draw an ADC like this, it can either be flash or it can either be SAR. The basic principle will be valid for both of them, just that the circuit implementation will differ. Cool. Now let's see if we can come up with some technique so that we can get a higher resolution. So for that, let me take a look at the ADC. So in the ADC, first we sample the input. So let us say I sample the input y of n. After sampling, what do we do? Quantize. And what is the simplest mathematical model for quantization? You add a quantization noise. Let us say this is some q1 of n. So the output v1 of n is y of n plus q1 of n. Fine. Now ideally at the output, what do you want v1 of n to be? We just want y of n, right? Now forget that this is an ADC. Let's say you have selective amnesia, you forgot that this is an ADC. Assume that this is some random system you have. At the output, all I want is just y of n. Right? So what can I put in between here so that I get only y of n? If I subtract, if I somehow go and subtract q1 of n, get y of n. Now you partially get your memory back. You say that, hey, this looks like an ADC. In an ADC, I can't access q of n. That is not an independent signal. What points I can tap in an ADC? I can tap either this or this. So how can I find q1 from these two? Yeah, so essentially if I go and subtract these two, what do I get here? Can you check carefully? What do you get exactly? So what can I do now? I'll basically go and connect it here. So now you get your full memory back. You realize that, hey, this is an ADC. So can you do this in practice? I mean, looks like this is an interesting idea. I can completely eliminate quantization noise. But what is the catch here? I mean, remember that at the input of the ADC is an analog signal. Output of the ADC is digital. So if I have to subtract it, I'll have to cross the domain, right? So I can basically do it in two ways. So either I can convert both of these to, I mean, this is analog, this is digital. I can either convert both to digital or convert one of them so that both are in analog and then do it. So let's say I convert this to digital. So if I want to convert this to digital, what do I have to do? You have to put one more ADC. So let's see if you do what happens. I put one more ADC, so I'll color code it so that green is all digital. So everything is digital now. Okay. So if this second ADC adds a quantization noise Q2, what will be the signal? Y plus Q2. So what will be the signal I get after subtraction? Yeah, Q2 minus Q1. So what will happen at the output? This is Q2 minus Q1. So this looks like this is nothing, no, we're not getting anything, so let's forget this. So let's try the other route. Let's try to convert this signal to analog. For converting this to analog, what do you need? That. And one nice thing here is, remember that this DAC here is not trying to take the digital data and trying to give a continuous time signal. Remember, this is all still samples. It is just taking digital code, let us say 1, 2, 3, etc., converting it to voltages like this. This can be done without any error. So that is one nice thing. This DAC, ideally, this doesn't add any error by itself. Right? So now you do this. I get minus Q1. You subtract this also in analog, this also analog. You get minus Q1. So you have this analog signal, but finally you have to add it in digital. So what you need to use here? You need to convert this to digital using another ADC. Now remember that the signal we have is minus Q1, right? Let's say this is a 3-bit ADC. So if this is a 3-bit ADC, again let's say the range of this ADC is from minus Vref to plus Vref. So what can you say about the step size delta 1 for this ADC? Yeah, 2 Vref by 8, right? I'll write as 2 Vref by 2 power 3. Fine. So what can you say about the range of values the quantization noise can take? Minus delta by 2 to plus delta by 2. So that's minus Vref by. So now you see that the signal that is, if I connect it directly, the signal going here is spanning a very small range, whereas the actual range for this is minus Vref to plus Vref. So to get the maximum performance out of this ADC, I need to make sure the signal here spans the entire range. So what should I do? What should I put in between? We have to put an amplifier. So you put an amplifier here. And what should be the gain of this amplifier here? 2 power 3. Okay. Let me actually erase this so that we can redraw it neatly. So now let us say this is the first output V1. Oops. So if I call this V2, what is V2? If let us say this has a quantization noise Q2, what is V2? Can you check carefully? Here it's minus Q1. So what is this one? So output is minus G times Q1. Now remember, we started with the goal of completely cancelling Q1. So I have two signals. How do I combine the two so that we get the final output? I have V1, V2. I should combine this in an appropriate manner so that Q1 completely cancels. No, I mean forget about circuit, just mathematically. Yeah.
Divided by something.
Yeah, basically you divide this by G. I mean the idea is here I added G, so you put 1 by G here so that it's same as, that's all. If I do this, what do I get? So this will be Y plus, this will be Y plus Q1. V2 is, so essentially you only get Y plus Q2 by G. Fine. So now at least you see that there is definitely an improvement because this gets divided by a factor G, and you can see how much is an improvement we get, right? So let us say for example the second ADC is 4 bits. So if I just have Q2 corresponds to an ADC with 4 bits of resolution. Now what I have is Q2 by G. G is 2 power 3. So Q2 by 2 power 3 will correspond to an ADC with how many bits of resolution? 7. How are you saying 7? Yeah, remember if the quantization noise Q2 can take a range from minus Vref by 2 power 4 to plus Vref by 2 power 4. If I divide it by 2 power 3, it becomes this. So this corresponds to 7 bits of resolution. Fine. So what we have done essentially is I have taken a 3-bit ADC, 4-bit ADC, put some magic blocks here and there, and eventually I see that I have an effective resolution of 7 bits. Yes. Random. This is a random choice. It can be anything. Just to give a numerical example, I took. So let me actually redraw this in a slightly more aesthetically pleasing way. So what I have is, I have the first ADC. So this is giving me 1. So my goal is to cancel the quantization noise of the first ADC. So how do I do that? How did I cancel the quantization noise? I took this, subtracted with the input, but for that first I need to have a DAC. I basically did the subtraction. Here I got minus Q1. Now, if I directly went and fed it to the second ADC, that would not mean, that would mean I'm not getting the maximum performance out of this. So I went and amplified it by a factor of 2 power 3 in this case, because I assume this is basically 3 bits. And then I gave it to the second ADC. So this is V2, right? And remember, I combined the output as V1 plus V2 by G, and that gave me the final thing as Q2 by G, right? So now if I start at the expression, I see that at the output, the quantization noise is getting divided by a gain G. So why can't I keep increasing this gain? Why not?
Be decided based upon that range of Q1.
Yeah, correct. We know that Q1 was in this case going from minus Vref by 2 power 3 to plus Vref by 2 power 3. Yeah, so what?
So that G is 2 power 3, that
correct.
Comes from the resolution of ADC.
If I increase, what happens?
Increase the resolution.
No, if I increase the gain, I have 3-bit, but still if I increase, let's say I choose a gain of 10 power 6, what happens? From here it looks like it's fine, so what's the issue? Huh? If I use a gain greater than 2 power 3, what can you say about the signal swings here?
Be larger.
It will exceed its full scale range, so which means the ADC will kind of saturate. This entire exercise is based on the assumption that I'm getting an estimate of Q1 in the digital domain and cancelling it. If I have a case wherein the signal here exceeds the full scale range, then the ADC2 will not be able to faithfully reproduce Q1. So the maximum gain I can have here is what? So here the maximum gain I can have is 2 power 3. So this is really crucial. You have to ensure that the signal swings here is within the range for the second ADC. Otherwise, this entire principle will miserably fail. So,
Sir, ADC1 samples was at T0. It will take some time for the.
We'll come to the timing things in a moment. Okay.
So that way, the difference is not a good estimate of Q1.
No, we'll come to how it's going to do the. We'll come to exactly at what time instance each ADC will operate in some time. Okay. Let's not worry about it. Let's say that's taken care of. Cool. So yeah, this is the maximum gain. But remember that I can also use a gain smaller than this. Still fine. But if I use a smaller gain, then I'm not squeezing the maximum SNR from the second ADC. Right? So as of now, if I use gain of 2 power 3, what is the effective resolution I get?
7.
I got basically right? Now if, so let us say now if I use a general gain of G, right, what will be the effective gain?
T plus log.
remember how we came up to this distance of 7 bits, because at the output I had Q2 by G. If G was 2 power 3, this was 4 bits. He told it is 4 plus 3. Now what I am saying is, it is Q2 still coming from 4 bits, it is some general gain G. What will be this 4 plus? Log base 2 of G. So that's a general thing you give. Okay. Now I can basically generalize it. I can have, let us say, a B1 bit first ADC, B2 bit second ADC. In that case, what is the maximum gain I can have? If the first ADC is B1 bits, what is the maximum gain I can have? This basically. Okay. And as usual, I combine the output as V1 plus V2 by the gain G. And what is the effective resolution I get in that case? Now can you check carefully? Remember that it is Q2 by G, so it is the second ADC and the gain here. So it is B2 plus log to the base 2 of. So again, it's a new thing. You keep a name, and this is called two-step ADC for obvious reasons. So here the point to notice, the effective resolution here depends only on the last ADC you have and the gain you use here. Right? So how is the first ADC affecting this expression finally?
Affects the maximum value.
It just sets the maximum value of gain G, that's all. Otherwise this first ADC plays no role. It is just setting an upper limit on G. So the final resolution only depends on this fellow and the gain you have. And the important thing to notice, this swing here must be within the range for the second ADC, otherwise it gets screwed up. Okay. So now let's actually see how we can go and do this business, V1 plus V2 by G. For that, I'll take the same case. I assume that V1 is 3 bits, V2 is 4 bits. So let us say V1 is X1, X2, X3. V2 is say Y1, Y2, Y3, Y4, 4 bits. Now what I have to do, V1 plus V2 by 2 power 3. Fine. Now let us say first you want to understand how you can even do V1 plus V2. Now remember, there are two ways in which you can do this. I can write it like this, or I can write it like this. Basically, in the first case, I am aligning the MSBs, second case the LSBs. Which one do you think is the appropriate way? Why not? Why second one?
You are multiplying with the same to the power 0. X3 are multiplying with the
Okay,
power
think
0.
about it. The first bit here, it is giving information. I mean, let us say it's starting from 0 to V. If I know that the first bit is 1, what can I say about the input voltage? It is basically in the upper half, right? Irrespective of it's a 3 bit or a 4 bit, the first bit here, X1 or Y1, that tells you whether the input is in the upper half or the lower half, right? So which means what should you be actually aligning? Should be aligning the LSBs or the MSBs? MSBs, because these two bits are giving the same set of information. See, other way to see is, let us say it is a you can use it to represent both positive and negative numbers. So it's instead of going from 0 to 7 for a 3-bit case, I encode it as -3 to +3, right? So which means the first bit, I have, let us say, something like this. If this can take both positive and negative numbers, the first bit, what will it tell you? Whether it is positive or negative. First bit is the sign bit, right? So let us say you have one number like this, other number like this, more bits. So this is giving the sign bit. You basically have to align the sign bit. So the correct way to align it is, so let's quickly see. I have to write V1. V1 is x1, x2, x3. This is V1. V2 is basically y1, y2, y3, y4. But I want V2 by 2 power 3. How will V2 by 2 power 3 look like? Dividing by 2 is basically right shifting. I am right shifting by 3 times. Fine. So if I write V1, it's x1, x2, x3. If I add these two, what do I get? Yeah, it's basically x1, x2, x3, y1, y2, y3.
Basically V1 is the input signal passed to the second ADC, but the final bit will be at 0 because the first ADC does not have that resolution.
I am not following. V1 is the output of the first ADC.
V1 is the input passed to the first ADC, but if we think it's 4 bits, then the final bit is 0 because the first ADC does not have that resolution to get that final bit.
No, I'm not following. I mean, the idea is, we'll discuss it maybe, I'm not understanding it clearly, but the operation we have to do is this, right? To cancel the quantization of the first ADC. And for that, when I shift it by exactly 3, it basically gives you 3 zeros. And the addition is very trivial here. You take the 3 bits of the first ADC, 4 bits of the second ADC, just pad the 2, and you are set.
Resolution is increasing by 4.
Yeah, 7 bits, right? Effectively, you want 7 bits, that's what you get. Okay. So I can generalize it. Now if I have the same case, B1 bits and B2 bits, and if I choose a maximum gain 2 power B1, even the final thing will be this. I just take V1, V2, append it like this. This gives you the final V. So now you have two-step ADC. You can basically keep extending it. You can make a 3-step ADC. Let's just generalize it and we'll wrap today. So how can you form a 3-step ADC now? Can you give me a hint? I know how to make a 2-step ADC. I want to extend it by one more step. How can I do? No, yeah, but okay, V2 passes through a DAC and
Then again subtracting with the input of ADC to
yeah, I mean, simple thing is, see, this again recursion, right? I have 2 ADCs, 2-step ADC. If I want to make a 3-step, I'll assume this itself is a 2-step ADC, right? That's all. So that's what I'm trying to do now. So what I've drawn here, let's assume this is the second ADC itself. This is one whole ADC. This will be treated as my second ADC later. So let's say if this is Y, let's say this is ADC2, DAC2, ADC3. So this will give you minus Q2. Let us say this has B2 bits of resolution, B3 bits of resolution. What is the gain you choose here? To the power B2. Fine. And let me actually erase it. Make some space. Let us say this is V2 and V3. So the effective output of this ADC is V2 plus V3 by, let's say it's G2. Fine. And if I do this, what will I get at the output? Let's say the input to this is Y. What will happen at the output? I'll have Y. Yeah, let's say the quantization now is Q2 and Q3. What happens? Q3 by. Fine. So now let's treat it as one ADC as a whole. Now I am going to use this as the second ADC in my usual 2-step ADC, right? So which means I'll basically do the same thing as before. The first ADC is here. Let us say having V1 bits of resolution, quantization noise of Q1. Now my goal is to cancel the quantization noise of this fellow. So I'll take this, pass it through a DAC, subtract it, and what should I do after subtraction? I should amplify it. What is the gain I will use? 2 power b. Now let us say this is one whole ADC whose output is V2 hat. This output is V1. So how will I combine the final output as? V2 hat by, this is first ADC V1 and this is the entire second ADC V2 hat. Fine. Now let me erase the yellow box, easy to visualize. And now let's keep writing signals here. So this is going to be minus Q1, this will be minus G1 times Q1. So the input to the second ADC is no longer Y, it's minus G1 times Q1. So if I substitute this, I will basically have V1, V2 hat is V2 plus V3 by G2. Fine. If I do that, what do I get? I have V1 plus this fellow by G1. So what do I get? Okay, let's tell me in terms of V2, V3 plus now of course I also know V2 hat in terms of the actual signals, right? So this signal is getting divided by G1. What will I get? So it's going to be V1 plus minus Q1 plus, and what is V1 here? This is the input Y. What is V1 in terms of the input? So if I do this, I'll essentially get Y. So essentially if I do this, I see that the quantization noise of the first two stages completely cancel. I only have the last stage quantization noise that is getting divided by the overall gain you have in the entire path. So which means if I choose the maximum gains here, 2 power V1 and 2 power V2, what is the effective resolution? Q3 is coming from an ADC with B3 bits of resolution plus, right? In general it's B3 plus log to the base 2 of the gain you have. So this is how you do a 3-step ADC and you can extend it. So I'll just, is this fine? The idea is clear? So before we extend, there are a couple of jargons for you to remember. I'll just mention that. So typically the first ADC, we call it as the coarse ADC, or we can sometimes say it as front-end ADC. So if the first one is coarse ADC, what will be the last one? Fine ADC, or we say it's back-end ADC. And the subtracted signal, we call it as the residue. So which means the amplifier which amplifies the residue, what will I call it? That's all. And if I can basically extend it to n steps also, right? So let's just write that. So let us say I have n steps, okay, and let us say in the kth step I have an ADC with dk bits of resolution, and the gain I use is gk, which is 2 power bk, and the output is vk. So now recollect from for a 3-step case, I combine the outputs as V1, V2 by G1, V3 by G1, G2. If I have an n steps, how will I combine the output as V2 by G1, V3 by G1, G2 plus V4 by G1, G2, G3 plus blah 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 Vn by just an extension. And if I do this, the quantization noise of all the n-1 ADCs cancel. I'll get the first signal plus the n stage thing by, and the effective resolution I get will be, this is the final output. What is the effective resolution I have? I mean Qn corresponds to an ADC with, yeah, I mean Qn comes from an ADC with Bn bits of resolution. So this will be Bn plus, let us say in general, log to the base 2 and even this addition operation is trivial. You just take all the data V1, V2, V3 and just keep padding them to get the final results. So just to answer one question that he asked, see, now the thing is there are two ways in which you can go about doing this, right? So let us say I have the first ADC, ADC1, ADC2, ADC3. Let us say first input is processed by the first ADC. It digitizes it and gives the output at first clock edge. Now one thing you can do is you can wait so that this is then processed by the second ADC, the quantization noise, and the second ADC gives the output at the second clock edge. And after the second ADC does the comparison, you find the quantization noise of the second ADC, give it to the third ADC and do this, and then you can start the second input. So this is also something you can do, but if I do this, I finish one comparison in every 3 clock periods. So is there something smarter you can do? Yeah, I mean you'd have learnt in probably some kind of computer course. So by the time the second ADC is processing the first input, no need to keep these two guys free. I mean no need to keep this guy free. I'll ask this guy to process the second input. So which means second input will be done here. So this can take the third input. So this way, at every clock edge you get an output. The first, the first signal comes after third clock period, but in the fourth clock period I can get the second output. And this, what is this technique called? Pipelining. And when we do this, this is called the pipeline ADC. So whatever we saw, the same multi-step n-step ADC, if you kind of pipeline the operations, that will be pipeline ADC. But only one catch when you do that. So let us say at this point, right, you see that the first ADC is processing the third input, second ADC second input, first ADC is the first input. So if you want to get the reconstruct, V1 plus V2 by G1 plus V3 by G1 G2, this should be delayed and taken, because the first ADC had processed the first input 2 clock cycles before, second ADC had processed the first input 1 clock cycle before. Okay. So you cannot simply say that I'll take V1, V2, V3 is there. I simply cannot say I'll take 1 by G1, 1 by G1 G2 and add it. Because there is a delay, you have to have 2 clock cycles of delay in the first path, 1 clock cycle of delay in the second path, third part do it, and then you kind of scale it. So when you reconstruct the signal, this is something you need to take. But yeah, this is the basic idea of pipeline ADC. The final point to remember is, when you do this entire business, the quantization noise of all the previous stages completely cancel. Only the backend ADC's quantization noise remains. That gets scaled by the entire gain you have previously. And the maximum gain you choose will be dependent on the previous stage ADC to power the resolution of that. And the effective resolution is this. And when you use the maximum gain, even the final summation is trivial. You just keep adding all the bits to get the final bits. Sorry, I exceeded a lot of time. I'll stop here.